Good afternoon, everyone. Today we'll continue with our discussion of op-amp or operational amplifiers. There's a few more slides to go through. Today we'll look at non-inverting amplifier and the derivation for the gain of a non-inverting configuration. And then if you have time, we'll also get into the inverting configuration. Okay, so let's go to our notebook and then I will explain the terms that I just spoke about. So we had stopped here. All right, voltage transfer characteristic of an op-amp first. So the output of an op-amp, an operational amplifier, let's see, where's my pen? Can either sink or source current. We've talked about that. For today's talk and for the next class also, we'll talk more in terms of the voltage gain of an operational amplifier. Okay, so gain is noted with the symbol A, uppercase A. Okay, and then voltage gain in general is noted as AV, subscript of uppercase V. Okay. And then in an op-amp, we spoke about how we can take the output and we can feed it back into the input terminals, whether in the inverting or the non-inverting input, right? V in minus or V in plus. So if we take the output and feed it back, we call that a feedback loop, or we also refer to it as closed loop. So the output is being connected back to the input. That's a feedback loop, meaning it's a closed loop. Okay. So CL stands for closed loop. And if there is no feedback, we refer to it as OL. And OL would be open loop. Okay. All right. So these are just some of the terms that we need to understand before we begin any other discussion of, or before we discuss any of the derivations. Okay. Gain is represented with uppercase A, voltage gain with AV. CL means closed loop. OL means open loop. Now, one of the most important properties of an op-amp or an ideal op-amp is that the open loop gain is infinite. Okay. Open loop gain is infinite, meaning we could feed it like 0.1 millivolts or something and multiply it by infinity. That's, of course, for an ideal op-amp. So AOL stands for open loop gain. And for an ideal op-amp, AOL is infinite, which of course is not true for a real life op-amp. But even having said that, the open loop gain for even a real life op-amp is very, 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 very high. Okay, more than 100,000 or so. So ideal op-amp, it's infinity, but a real op-amp or practical op-amps, the gain is also very, very high. And that's where we will begin. The output voltage for an op-amp in an amplifier configuration is very sensitive to any change in the differential input that is applied at the input terminals. So we have in plus, this in plus is referred to as the non-inverting terminal. And in minus is referred to as the inverting terminal. Okay. And they're, of course, noted by this plus and minus sign inside the triangle. Okay. So by its very design, by its very nature, if you will, the op-amp will amplify the difference between the two input terminals. And so we have this equation where V out is AOL times VID. VID is the differential input voltage. Which simply can be calculated from V in plus minus V in minus. Okay, so it's simply AOL times the differential voltage is V in plus minus V in minus. Non-inverting terminal minus the inverting terminal. So if we plot the voltage transfer characteristic, meaning how is the input voltage being transferred to the output? Well, V out will always be a multiple of V in. Multiple would be the gain A, right? So if you send in V in, you would expect it to be amplified and sent to the output, and you will obtain a linear line like here. You send in V in, output will be a multiple of that voltage. So it behaves like a voltage source. You're sending in some voltage, and the output follows the input voltage. Hence, linear relationship. So no matter what input it is, output is going to follow that linear relationship, simply multiplied by the gain A. And of course, the energy to do so is not infinite. There is a finite limit. There's an upper cap on it, and that comes from the power supplies. VDD and VSS, the plus minus dual power supplies. That's the upper limit. That's the lower limit. Okay. So once the output reaches that upper limit, it's going to flatline. No matter how much you increase V in, your output is going to remain constant at that line. It cannot keep increasing indefinitely. Does that make sense to everyone? Yes. Very good question. So the question being asked is, how come it does not reach the line? It gets close, but does not reach the line. The answer is the power required to run the op-amp also comes from VDD and VSS. So a lot of the voltage from VDD and VSS is dropped inside the op-amp itself. We can go back to the circuitry right here. I think one of the first slides right here. So this is a simple circuit configuration, but you can see the number of components and the resistors in there. So a lot of the energy that is supplied from VDD and VSS drops inside the op-amp itself. And so the output will never reach those limits of VDD or the actual values of VDD and VSS. It'll always be a little bit below, always. Does that answer your question? Yeah, okay. All right, so any other questions? Yes. So gain, question being asked is what is gain and what is voltage gain? So gain is basically the ratio of output to input. Another good question. What is the gain? It's simply the ratio of output to input. And then voltage gain, of course, would be the output voltage over the input voltage. Similarly, we also have current gain. We also have power gain. Okay. And so in terms of amplifiers, we can have voltage amplifiers that would amplify mostly the voltage, not so much the current. We have current amplifiers that would amplify currents. And we have power amplifiers that amplify both current as well as voltage. Make sense? Okay. Since we are talking about amplification so much, let me go on just a slight tangent and talk about what an amplifier is and what it actually does, right? When we talk about amplifiers in electrical engineering or just even in general, what we are talking about is taking an AC signal so an AC signal that might be, let's see, it'll be very small. Say AC, and then you'd have a very large DC energy source. So we'd say a DC energy let's say greater than, I think greater than 10 volts, but in real life could be anything. 10 volts is just a random number. Okay, it could even just be 5 volts. And this, let's say, is approximately typically in millivolts. So the question is, let's say an op amp has a voltage gain of 100. If we apply 1 volt to it, do we get 100 volts at the output? And I think I touched on this a little bit, or maybe not. Okay, let's say an op amp has, or any kind of amplifier, has a gain of 100. If you apply 0.1 volts to it, what do we expect at the output? 0.1 times 100, 10 volts. How about if we give 1 volt at the input? All right, how about 100 volts, right? But do we really expect to obtain 1,000 volts from an op amp circuit? The energy does not come from thin air. The energy must come from somewhere. So the energy to amplify any quantity, whether it's voltage or current or power, comes from a DC source. Okay. So the simplest way I like to put it is that an amplifier would take an AC signal and give it, it would take the DC source and give it the shape of an AC signal. Okay, so it takes the energy from the DC source and gives it the shape of the AC signal. The AC signal, for simple representation, is simply one sine wave that I've shown here. Could be anything. If you think about it, the sound of my voice that is being captured by the microphone right now, microphone converts it into, sound waves are converted into electrical signals. Those are very, very small. There's a preamplifier circuit in there that would amplify the current a little bit, so it makes it a little bit stronger, modulates it, transmits it wirelessly, goes into our amplifier system, and the amplifier system takes that electrical signal, amplifies it again, so now imparting more voltage or more current to it. And the power to do that comes from either the battery that's inside the device, or if it's the computer, then it comes from the DC power source that's inside the computer. Okay, so any amplifier, the energy to work comes from the DC source. So you take the AC signal and you give it the energy from the DC source, and that's why there's an upper limit. If your DC source is only 5 volts, we can never have more than 5 volts coming out. Okay, if it's 10 volts, we can never have more than 10. If we apply 25 volts, we can expect output to go up to 25. Well, minus the internal consumption of the op amp, of course. All right. Make sense? Let's take a pause. Let me know if you have any questions. Okay. All right. So we're talking about how the op-amp can supply a output voltage, right? That means it can function as a voltage source. And if it can function as a voltage source, depending on what is controlling that voltage, we can model the op-amp as a dependent voltage source that is controlled by the input voltage. And so we can build a voltage control voltage source using an op-amp. Okay. In simpler terms, this circuit is also known as a non-inverting amplifier. Because Vin, the source voltage, Vs, the source voltage, is fed into the non-inverting terminal, the plus sign. Okay, it is fed into the non-inverting terminal. Right here. Going into the non-inverting terminal. Hence, it is known as a non-inverting amplifier. This is something that you'll study later on, AC analysis, not in 115. But if you feed in a signal like this, and the output has the same, well, actually, let's write down input. And let's call this this is known as the phase of the waveform. If the output has the same phase, it is known as non-inverting. This is for AC, not for DC. And if positive turns to negative and negative turns to positive, then we say output is inverted or inverting. Technically, this is known as 180 degrees out of phase. In simple voltage terms, a positive value of the voltage is inverted to negative value. That's how we get a 180 degrees out of phase waveform. Okay, so we are going to look at non-inverting amplifier right now. And after this, we look at inverting amplifier. The difference between the two is that the input is fed into the into the non-inverting terminal. Then we get a non-inverting amplifier. We feed it into the inverting terminal, we get a inverting amplifier. Right? Non-inverting amplifier, the applications might be quite obvious, but I'll give you an example of inverting amplifiers or why an inversion is done. One of the most common applications for a inverting amplifier is in noise cancellation. An AC signal is out of phase by 180, and you add that 180 degrees inverted signal to the original input, the resulting answer is equal to 0. And that's used for noise cancellation. Even before you had noise cancellation headphones, even the earliest phones, wireless cell phones or any kind of communication device, had a small microphone near the speaker. So that microphone would capture the ambient noise around the speaker. It would capture, invert it by 180 degrees, and then add it to that original input. And thus, the speaker is only sending out the output signals that is being fed through the lines. Any ambient noise is canceled out. And that is the operating principle of a noise canceling headphones. Anyway, coming back to our topic here. Non-inverting terminal, we have the output fed back into the inverting terminal. So this is an example of negative feedback. Negative feedback. And if you look closely, you can realize that this is a voltage divider network. It's a voltage divider network, R1 and R2, right? V out, R2, and R1. And so a portion of that output is fed back into the input from the middle terminal, and then middle terminal out. Actually, let's see. It should be V out times R1 over R1 plus R2. Okay. So we are applying negative feedback, meaning we're trying to reduce the difference in the input. It's a voltage divider network. Comprised of two resistors, R1 and R2. And then you obtain an amplified or larger signal at the output. Okay, V out will have an equation of R1 plus R2 over R1 times V in. And V in this case is our Vs of t. Okay. So V out, the V out expression for a non-inverting amplifier is R1 plus R2 over R1. I'll write the more common form from an expression. So if you're reading a textbook, you'll see this. 1 plus R2 over R1 times V in. Okay, 1 plus R2 over R1 times V in. So then let's see how we arrive at this expression. This is a more common form that you would encounter. Okay. All right. So the theory for this is that the input currents are so small that we assume them to be negligible and close to zero. Okay. When we say input current, you're talking about the current that is coming from the AC voltage supply, the AC signal that we wish to amplify. Typically, those signals are very small, so the currents are going to be very, very small. In an ideal op amp, it is zero. So if we analyze circuits using ideal op amps, input currents are zero. In this case, they're negligible, so we assume them to be zero. And so the input current going in right here is going to cause negligible voltage drop across RS. Okay. Then the reason we say that the input current is zero is because the op amp input resistance is very large. Okay. Between the differential input terminals, the resistance that is modeled is very large. That is another property of a op amp. So if we use these two properties and apply it to the voltage divider network, we obtain an expression for V in minus, right? V in minus is the amount that is being fed from the output that we just saw on the previous slide. Right? V out times R1 over R1 plus R2. And so V in minus, right here. Let's do the other way around. Is going in there. And that V in minus is right here. Okay. A small portion of V out is fed back into the inverting input. Now let's designate R1 over R1 plus R2 as F, notation F for feedback ratio. Okay, so F is equal to R1 over R1 plus R2. Therefore, 1 over F is going to be R1 plus R2 over R1. Okay. Now, what is the property of the op-amp? The property of the op-amp is that it will amplify the differential input voltage, right? So the differential input voltage is V in plus minus of V in minus. Multiplied by the open loop gain AOL, right? V in minus, we plug in from the we plug in V in minus from the divider expression that is right here. So we get F times V out. Okay, F times V out. We open this up and we obtain AOL times V in plus minus AOL times F times V out. We take V out on the other side and we obtain this is equal to AOL times V in plus. Rearrange all the terms and we obtain an expression for the output voltage as AOL divided by 1 plus F AOL times V in plus. Okay, this is in terms of the open loop gain, but we are not functioning in open loop. We are functioning in closed loop mode. So we need to convert this, and that's something we'll do on the next slide. But let's take a pause. Let me know if you have any questions thus far. Yes. So where on this diagram, question being asked is where on this diagram would be able to see RID? RID is typically modeled right here. That's the internal resistance between the two external terminals, in plus and in minus. As you go along in higher classes like 215, you will learn the term impedance. And so this term here where it says input resistance may be referred to as input impedance. If you read any sources or any books, whether on the internet or anywhere, instead of resistance, you will come across the term impedance. For now, understand that they can be used synonymously, whether it says impedance or whether it says resistance. As far as we are concerned, it means one and the same thing. Technically, they are two different things, but for this purposes, it's the one and the same thing. Okay, but that's where it is modeled at. All right, any other questions? Okay. So, excuse me. V out is AOL times V in plus minus V in minus. We obtain an expression right here. AOL over 1 plus F AOL. Well, open loop gain, ideal op amp is infinite. Real life op amp is still very, very high. So F times AOL is going to be far greater than 1. So we can ignore that 1. And hence, we obtain an expression 1 over F times V in. And 1 over F is R1 plus R2 over R1 times V in. So V out is V in multiplied by the ratio of the feedback resistors, R1 and R2. Okay, R1 and R2. Let's take a pause. Let me know if you have any questions. Any questions? Okay, so we have an expression for V out, right? So V out is equal to, let me write it right up here. R1 plus R2 or R1 times V in. If we take V in on the other side, we get V out or V in is equal to R1 plus R2 over R1. V out over V in is the voltage gain AV. You can also describe this as closed loop gain ACL. And write this R1 plus R2 over R1. Or the more common form, the gain of an non-inverting amplifier is given by 1 plus R2 or R1. R2 sometimes is also referred to as RF feedback resistor. And R1 is sometimes referred to as RI, the input resistor. Okay, so we can use resistors and we can design the gain of an amplifier using an op-amp chip. Have you all done this in the lab? Some nods, 1 or 2 nods. That's it. Yes, no, okay. All right, let's take a pause. Let me know if you have any questions. Yes. Oh, that's the design of the op-amp. That's something that we don't, well, not until like 400 level classes. Okay. So let's look at a SPICE simulation. This is something that, again, students are strongly advised that they can run at your own end. You have a op-amp, LT1457, typical standard op-amp. LT doesn't have many of the other ones. But we are applying a sine wave, 50 millivolt offset with 100 millivolts peak to peak. And let's see, perform analysis for like 0 to 3 milliseconds in steps of 1 microsecond each. VDD and VSS is set to 5 volts. So actually, the power supply rails go between plus and minus 5 volts. This is another way of doing LT-SPICE where you, instead of doing cross connections of complicated circuits, you break it up into individual parts and you simply name those terminals. And it automatically makes the connections. Okay, there does not have to be a physical line joining them. All right, so we are designing an op-amp with 2 resistors, 51K and 2K. We calculate the gain from here, 1 plus R2 over R1. Well, you get 2 over 52, 26.5 is our gain. So any input we feed into the amplifier will be multiplied 26.5 times. You're given 1 millivolt at the input, your output will be 26.5 millivolts. If you give in 100 millivolts at the input, output's multiplied by 26.5 times, so we should get a 2.65 volt sine wave, both positive as well as negative. So total swing of over 5. There's a DC offset of 50 millivolts. So that DC is multiplied 2. So if you look at your waveform, the output waveform, let me like zoom in to the waveform a little bit. Instead of being centered around 0, your input waveform itself has a DC offset of 50 millivolts. Let me write down DC offset. So your op-amp is going to amplify that DC signal also, right? And so at 50 millivolts, that's the 0 line. That's the actual line. Shifted upwards by 1.3 volts, right? So if you're designing this for an audio application and you don't want the DC voltage going in there, so we have to remove the DC offset before we send it in. The point being here is that whatever voltage you send in at the input is going to be amplified. If it's DC, it's going to amplify DC. If it's AC, it's going to amplify AC. So this example shows you both. You send in DC plus AC, it's going to amplify both. Right? So the DC offset of 50 millivolts is now changed to 1.3 volts. In your AC output is swinging between these two lines right there. But what's happening over there? It's getting clipped. It's reaching a saturation level, and hence it's getting clipped. So saturated or clipped. And the reason for that is it is hitting the upper limits of the power supply. You can see here it does cross 3 volts. So we obtain 3.1, 3.2-ish, 3.2 maybe. right here, and then it clips. So the rest of the voltage is dropping inside the op amp. So the power supply, the DC power supply is not sufficient to amplify the signal because you're only applying plus minus 5 volts with a gain of 26.5, right? So you have a very small signal, you're amplifying it, but the container to fit that is far smaller. And so it's clipping off the top. That's what's happening. So if you wish to amplify or obtain the full potential, then we apply a larger voltage. So we apply plus minus 10 volts, and now you get the full swing per output. Your zero line is here. It's the DC offset, and that's your full line. That's like going all the way to 4. Okay. This is an easy simulation that students can replicate. So, strongly urge you to do that. Okay. Take an op amp, connect it in a non-inverting configuration, apply an input voltage. You can play around with the parameters, apply a DC offset, positive offset, as is shown here in the slide. You can apply a negative offset. You can also remove the offset completely and see how the output changes for different DC voltages. Okay. All right, let's take a pause. Let me know if you have questions. Yes. So question being asked is, why is it getting clipped at 3.2 volts and not at 5 volts? The answer is that portion is dropped inside the op amp itself. So it's consumed. So the op amp is created with multiple transistors, resistors, capacitors, and that entire thing is known as an op amp. So all of that energy that is missing from here is consumed within that op amp. If we didn't have the offset, let's see, if we didn't have the offset, then perhaps it would work just fine. You would still have the full output. Yes. Why are we using, so the question being asked is where? Oh, here, RS. That's a random value, just to show that's a very large resistance and very small current is actually going in. So to model, if you make it very small, then chances are a lot of the input voltage could drop across that resistor. So we want the input current going into the op amp very, very small. So we just modeled it as a very large resistor at the input. Question being asked is about this RS resistance and why is it large? It's so that we can actually say that the input current going in is very, very small. Okay. All right, any other questions? Which op amp chip did you use in the lab? Which one, like numbers? 358, LM358. No, I thought that was a comparator. Was that an op amp? Okay. All right. Okay. Let's see. So then let's look at oh yeah, before we look at inverting amplifier, non-inverting amplifier, some properties. Okay, so non-inverting amplifier or even an amplifier in general, sorry, an op amp in general has very high input resistance and very low output resistance. Here's the thing to keep in mind. When you read up about op amps, it will say that ideal op amps have a few properties. It has infinite open loop gain, very high or infinite input impedance, input resistance, zero output resistance or zero output impedance, right? When we create circuits using these op amps, those parameters will change a bit. So when we talk about parameters using this configuration, we are specifically referring to the non-inverting amplifier, not the op amp itself. Again, in general, for an op amp, we say that op amp has infinite open loop gain or very high open loop gain. We say the op amp has high input resistance and low output resistance. But here we are talking about the circuit that is created using the op amp. So we are talking about non-inverting amplifier, not the op amp itself. So the non-inverting amplifier created with the op amp also has very high input resistance. So it is not a given that any circuit you create with an op amp will have high input resistance. It depends on how we configure the circuit. In this case, we are taking the output and feeding it back into the input, a negative loop. So non-inverting amplifier still has very high input resistance. Okay, it draws very little current, and we have about 3 minutes. And the input current can also be modeled as charging a capacitor. Okay, and that's shown right here. On the output side, output has low resistance and it can power a source, meaning if it has low resistance, it can send source out current. And so it can connect, it can be connected to loads that require output current from the amplifier. So we can use the op amp as a voltage amplifier or as a current amplifier or as a power amplifier. Okay, because it has low output resistance. Low output resistance means high output current. So it can source or sink high output current. Here, I just want to point out the dot step parameter, or PARAM in LT-Spice or Spice, allows you to impart steps to a certain variable. So in this case, we are saying that R load right here, the variable R load, is going to have 3 separate values: 1K, 250, and 75 ohms. And so LT-Spice simulates or runs 3 simulations using those 3 values for output load resistance. Okay, and then you can see the results here. Let's see, 1 more minute. Actually, you know what? Let's just stop. Let's stop right these 2 slides, and then we'll pick up here again on Friday. Okay. In the meantime, if anyone has any questions, I'm happy to answer them. But we'll end class here today. Any questions? Okay. If you have some time, sit down and just run a simulation with the op amp in LT-Spice and see if you can duplicate the results.